Next speaker is Sylvestre Lacour from LESIA. He will talk about the interferometry detection of exoplanet and characterization. Sylvestre, are you online?
Yes. I'm just here. Right. Up. Can you see my slides?
Yes, it's still in presenter mode.
Okay. Good.
Okay, go ahead.
Okay, so now I'm going to talk about exoplanets, and this talk is about the observation of exoplanets with gravity, and it's on behalf of a team of researchers, including people working on gravity, but other people who joined that team to observe exoplanets with optical interferometry. And just I want to advertise that you can join us if you want to, if you need help for technical details. We are also here to provide help if you want to go into that field. So just a short, a few slides of context. Of course, you all know this slide with the different technique and the mass as a function of separation. But when you do optical interferometry, when you try to directly observe exoplanets, what matters is this diagram, which is here the contrast ratio as a function of the angular separation in the sky. And you see that most of the known techniques like transit and radial velocities are actually observing planets which are too faint to be observed by direct imaging. It's because of this slope here that you see in gray, that's the expected rate of planets within 30 parsec. The vast majority of these targets are cold enough, so in the infrared, they just emit reflected light from their star. So that's why you have this slope. You have an exception, which is beta Pictoris C. I'm going to talk later about that. And to the upper right, all the known exoplanets directly observed by classical imaging. And if they are up there in the diagram, it's because they are hot. They are still very young. They still have the formation entropy, the energy of the formation entropy of the exoplanet. So they are still of the order of 1,000 Kelvin. And we expect many of other planets to be that hot, and that could be observed. So that's a simulation here of what we could expect of exoplanet younger than 10 million years in pink and a few 100 million years in blue. And the gravity instrument here is very interesting because it reached this zone around the ice line where we expect most of the young Jupiter are. So that's the field of view of the domain of observation of gravity, which is at shorter angular separation compared to classical imaging. So what does it take to observe an exoplanet with an optical interferometer? Well, it's not just one beam combiner. It's actually two beam combiner, one for the French tracker and one for the science. But it's also a full infrastructure. You need a metrology. You need to stabilize the pupil. You need adaptive optics, and it's not just a beam combiner on one side. Meanwhile, if you observe with gravity, if you look at the acquisition camera, that's the acquisition camera panel. When you observe in Paranal, you have this four column, which correspond to the four telescope. And the bottom row, you have the field of view of each one of the telescope. So they, of course, observe the same object. And you see that this field of view here is divided into two. So that's a part which is reserved for the French tracker, and a part which is reserved for the science beam combiner. Like I say, on gravity, you have the two interferometers. So if you zoom on that field and you try to observe, for example, a brown dwarf, here it's GQ loop B, which is at 700 milliarcton. So in a way, it's an easy example of observation of an exoplanet. What you do is that you position one part, the fringe tracker, on the star. So it's the upper right. So that's the field of the fringe tracker. The fringe tracker is centered on the star. And the science beam combiner, which will do that, which will do interferences on the brown dwarf, on the exoplanet, on the edge. And you do that because the contrast is so high that you need these two levels of correction to be able to detect the light from an exoplanet. Let me explain that to you by a simple diagram. So on the left, you have the two interferometers in red, so that the fringes observed on the fringe tracker on the star. So they are bright, they are shiny. And on the left, you have the faint fringes observed on the exoplanet or on the brown dwarf. So since you put the fiber of the exoplanet, the science fiber offsetted with respect to the star, you have less flux coming from the star within your science beam combiner. However, you still have lots of flux leakage coming from the star, but you can distinguish the photons coming from the star with respect to the photons coming from the exoplanets by looking at the fringe packet. So the fringe packet made by the interference on the star will be offsetted with respect to the one from the exoplanet, because the two objects are not at the same position on the sky. So that's a difference in position in the sky translate into an optical path delay, which shifts the two fringe packets, one with respect to the other, and which allow us to really see the photons coming from the exoplanet. Actually, if you look at the raw data sets, so that's an image on the right of the detector, you don't have a fringe packet. You don't have fringes. Actually, we're using A, B, C, D. We code a fringe in an A, B with 4 value, A, B, C, D, which is phase offset of pi/2. And we disperse that as a function of wavelengths. So for each baseline, you have 4 values, which code the fringes, dispersed over, like in medium resolution, we have dispersed over 200 spectral channels. And the data will look like that on the left. So from these 4 values, you can get a complex number. So that's what we call the current flux. This complex number has a phase, which is the phase of the fringes, and an amplitude, which is the amplitude of the fringes. And here to the left, so that's an observation of a brown dwarf again, to make the signal clearer to you. You have the blue curve, which is the data, this complex value I was talking about for each one of the 6 baseline. And the first thing we do is to try to remove the contribution from the stellar leakage. And we know what the stellar leakage is because we observe it also on the fringe tracker. And later on, we will be observing the star itself by positioning the fiber on the star. So we have a model of how would look the current flux on the star. For example, if you look at some feature like at 2.0 micron, you have the atmospheric, the telluric absorptions, and that can be quantified by observing the star itself. And from this observation, which happened just a few minutes later after our observation of the brown dwarf here, we can model both in amplitude and in phase the contribution of the stellar speckle. And this model is fitted to these complex visibilities, and you see them as the orange curve. So you can subtract the blue curve from the orange curve to remove the stellar contribution on the current flux on your detector. And then you get this value to the right. So now in blue, you have the current flux, both in real part and imaginary parts, seen on the detector after removing the stellar flux, the stellar speckle. And you see this oscillation here, which are due to the fact that the rest of the current flux is due to the Brandorf, which is offsetted with respect to the star, and which is in terms of OPD, which has a different optical path difference, as I said before. So it's the equivalent of having a shifted fringe packet, except here we see it as a function of wavelengths. So as a function of wavelengths, the visibilities, they spiral in phase like that. And this spiral here gives us exactly an optical path difference, very, very precise optical path difference between the position of the star with respect to the position of the Brandorf here. And that's how we can get both a very precise spectrum. So the spectrum of the Brandorf here is the amplitude of this current flux, and astrometric position, which is the frequency of these wiggles here, which give us an optical path difference. So when we first did this this observation on HR I799E, so that was 3 years ago. First, it came as a surprise because the gravity interferometer was not built to observe exoplanets. And then came the question about how to show the data, how to present the data. So I've been doing optical interferometry for now almost 20 years. And usually you plot the visibility curve, like for the Bessel function or the uniform disk visibility function. So the question was, what would you do for an exoplanet? And in that first paper, what we've plotted is the visibility with respect to the visibility of the star. So you can have different opinion on what's the best representation of the current flux you've seen on exoplanets. For HR 8799E, so we assume it's a point-like structure, so it's a point-like exoplanet at the resolution of the VLTI. So it's a constant, and you see it like that as a in the visibilities. So the dotted line is the error bar on the visibilities. But we've plotted them with respect to the flux on the star. So that's why you have this huge 10⁻⁴ difference in terms of visibilities. So that was what we did at the time. But then we observed more complex system like this one, PDS-70. So what do you do for PDS-70? What do you plot? Do you plot something, a visibility curve like that, or something different? Well, what we are interested in is actually the visibility of the planet itself. So PDS-70, well, everybody here knows what it is. It's a protoplanet. It's a few million years. So we are still, so we know that it's still accreting matter. We know that there's H-alpha emission, and we expect a large circumplanetary disk. And we want to to know if we can resolve this circumplanetary disk, which can be huge at the scale of this protoplanet. And to do that, you need a way to measure the visibility with respect to the flux of the exoplanet itself. So the first thing we did at the time, so we did the same thing as this plot here, where we normalize the visibility of the exoplanet PDS-70C and B with respect to the current flux observed on the star. So we had something similar to that, with, in addition, of course, the fact that the star is itself a little bit resolved. But that we can model it. We know how it looked like. So we correct the visibilities from the star, and then we used the observation, the sphere observation, which themselves give us a flux ratio between the flux observed on the exoplanet and the flux ratio on the star. And we use that as a ratio of incurrent flux between the exoplanet and the star. And that gives us the equivalent of visibility 1. So the one of the visibility here is unknown by our knowledge of the magnitude of the exoplanet, the uncertainty of the magnitude of the exoplanet observed by a sphere. But that gives us a 1. And then you take the visibilities, and once you correct that, you can plot them here. So since it's an object with exoplanet quite faint, we assume that the visibility is constant over all the wavelengths. So instead of plotting them as a function of wavelengths here, we just average the visibility, and we get these two panels for B and C, and we can then fit a model of a planet with a circumplanetary disk on this data. And of course, well, not of course, but in that case, we couldn't resolve anything. We assume we have an upper limit on the size of the exoplanet with its circumplanetary disk. So the third topic that we faced with the team is how to look for unknown planets. So I said in my first slide, it's here. Well, let's not get back to it. With gravity, we have the sensibility to observe exoplanets which are not seen by instruments like SPHERE or GPI. The problem is the field of view. The field of view of gravity is the field of view of a single mode fiber, which is the size of a point spread function. So you have to either pave the field of around the star, which is very time consuming, or you have to use some kind of assumption of where to look for. And in the case of beta pictoris system, so all of you know the beta pictoris system. In 2018, there was just one planet with a debris disk, so beta pictoris B. But in 2019, Anne-Marie Lagrange published radial velocity data. She was trying to determine the mass of beta pictoris B at the time. But what she's seen is that there was actually a higher frequency variation in her data. And this here that you've seen on the right, the radial velocity, point toward another planet with a period of 3 years. And if you know that you have an exoplanet with a period of 3 years, then you can zoom. So here, that's a zoom of the NACO image with B here on the upper left, which is something like 400 milliarc seconds. And we know that if we have an exoplanet orbiting with around beta pictoris with a period of 3 years, most likely the orbit will be in the same plane as beta pictoris B, and you could predict a position which will be around 100 milliarc seconds in 2020 for beta pictoris here, for beta pictoris C, which will be something here. And then we can start working with gravity and point toward that, knowing that, again, the field of view of gravity is of the order of 50 milliarc seconds. And we've done that in February 2020, and later again in March 2020. So here on the upper left, you have the NACO observation of beta pictoris B, and we found the beta pictoris C here. And even within 2 days, we could see the displacement of the exoplanet, which was of the order of 1 milliarc second. You see the accuracy here of the astrometry of gravity. As I said, it's a question of measuring the position, the phase of the fringes in the current flux. And that can be done well above the resolution of the interferometer itself. So that's how we can reach this accuracy of the order of a few tenths of microarc second. You see that the error bar, so this ellipsoid is a 1 sigma contour error bar. So it's not circular because the VLTI is actually elongated. So you have a UT1, UT4 baseline, which is longer than the other one. So that's why you have always this kind of ellipse in our astrometry, which matter a lot when we compute the orbital trajectories. But within 1 day, within 2 days, we could see the target by looking at where we expected the exoplanet to be. So we've observed it later. So we even have a measurement on the other side of the star now. We can precisely constrain the eccentricity, the semi-major axis with this observation. We can constrain the resonance effects between we can, of course, compute the period of each one of the planets. And we found that most likely the two exoplanets are in mean motion resonance of 7-1. So it's a faint resonance, but it's still there. And if the two planets are in resonance, the question was also, could we see the effect of one planet on the other? You know that that was 150 years, 170 years ago, Le Verrier found Neptune from the trajectory of Uranus, and we wanted to do something similar. Okay, so of course here we knew already that there was beta Pictoris C, but the question was, could we just with the astrometry of beta Pictoris B have predicted the position of beta Pictoris C? So same kind of work as Le Verrier did, but on an exoplanet system. And actually that's possible. So in this panel here, you have the trajectory of beta Pictoris B. So the measurement we've done with gravity, which are this red point here. So that's the system seen face on. And from this point here, you can fit a Keplerian orbit, and you can see the deviation in astrometry between the Keplerian orbit and the astrometry and the position of beta Pictoris B. And this oscillation here that you see, the deviation of the Keplerian orbit, is due to the fact that beta Pictoris C is rotating with a period of 3 years around the star. And by rotating around the star, the planet move the barycenter of the system, and the distance between B and the stars change. That can be computed using the Jacobi coordinate. If you go further, so Jacobi coordinate is just an approximation of a three-body interaction in a system like that. But if you go to n-body interaction, and assuming the mean motion resonance, you can also compute how would evolve the system in the future. And that's a work made by Hervé Bust, which can predict that. So first, we've seen that beta Pictoris C has a high eccentricity, and beta Pictoris C lower. And what we found out that beta Pictoris B could have eccentricity excited only from the eccentricity of beta Pictoris C. And then we get into the question of how did that system evolved. Could beta Pictoris B went through migration? Migration will have circularized its orbit, but then it will be excited by the eccentricity of the exoplanet C? That's a question. We're still working on it, but we are right now doing a similar analysis of the dynamics of the system as we've done on the exoplanet on the planet of our solar system 100 years ago. So it's quite interesting what we're doing here, just thanks from the accuracy of the astrometry. If you go to even more complex system like HR 8799, we could predict. So here it's a simulation. It's not using Jacobi coordinate. Jacobi coordinate, it's an assumption. Well, maybe it's a little bit complicated, but Jacobi coordinate, it's a change of reference where you assume that the central exoplanet perturbs the relative astrometry of the outer exoplanets. But here it's different. It's assuming that the outer exoplanets are perturbed by the central exoplanets. So it's a higher order, and we expect in a few years to be able to detect that signal. The second byproduct of our gravity observation are the spectrum. Of course, as I said, it's thanks to the angular resolution of gravity, you have a very precise way to disentangle the speckle light coming from the star. And by doing that, you can retrieve a very precise spectrum of your object. And from that, you can also probe molecules that could be done at lower spectral resolution as it was done by GPI, for example, or sphere. And by looking at this molecular absorption, you can compute, you can start to get into estimation the atomic component, the atomic ratio inside the atmosphere. So we are very far away from just measuring a column density here. We need a full model of the atmosphere. So that's part of our team who are specialized into that, to model the atmosphere, to predict this pressure temperature diagram, which is a fundamental step to predict the molecular concentration inside the atmosphere. But these are used to fit the spectrum, including the slope, which gives us the temperature, the roundness, which correspond to the water absorption on the side, and of course the C2O absorptions. And from that, we can derive the C2O ratio in the atmosphere of the exoplanet. So it's model dependent, but still our estimation are precise within 10%. Actually, we're doing 10. So here the C2O ratio is 0.45 plus or minus 0.05 on beta peak. And that's useful because it means that we can constrain the formation history of the exoplanets. So depending on how the exoplanet was formed, where it was formed, what process happened into the protoplanetary disk, we can estimate C2O ratio within the atmosphere of the exoplanets. And for the example, to the right here, so on the left, it's the same thing as before, but that's on the HR 8799E. And on the right, you have two different chemistry process happening into the protoplanetary disk. So one is the reset, the second one is ongoing. It's how the carbon is released into the gas. You can read the Alex Credon paper to know more about that. And by measuring the C2 atomic ratio of our exoplanet, we can constrain one or the other scenario of evolution of the protoplanetary disk and the exoplanet.
Sylvestre, are you almost finished? Because we are already over time.
You didn't follow. Okay. Yeah, I would like to spend. So that's done also on the HR 799 planets. I'm using 5 more minutes because I want to show you these results, which are ongoing results. So we've tried to do the same thing as we've done on Beta Pictoris B, but on Beta Pictoris C, but on a different system. In a different system, we have a few radial velocity from time to time, and we have a few, we have, of course, the Gaia DR3 data. And by combining these two, we can predict a position of an exoplanet. And that's the work we've done late last year, and it's soon to be published. We've predicted this position. So there was 2 family of position for the exoplanets. And we've used the different, we used dithering of the fiber to hunt for this exoplanet. So we've covered this red part because that was the more massive planet where we could hope to detect something. So we are looking where we could look actually. And you see that for each one of these observations, we had a chi-square map. And nothing really clear came up from the chi-square map. But we observed it, but we still have some kind of a small indication in our last observation below there. And we could observe it a month later at this position. And we've detected a new this exoplanet. And that's a paper which should be published in a few months. And it shows the power of gravity because often I was facing the question, oh, but with gravity, it's only about looking at exoplanets which were discovered by sphere. And no, now we can look for exoplanets using Gaia data. And here we'll have a result published soon about that. So here it's 12 Jupiter masses. Okay, so the future, of course, is a combination of Gaia and gravity we are working on. We have a large program ongoing. And stay tuned for the next observations. And you can contact us, of course, if you want help to go into the field. Thanks.
Thank you, Sylvestre. I'll take one quick question because we are ready. Yes, Jacques, microphone. Can you say your name and affiliation, please?
Yeah, so I'm Jacques Pluska from K11. Thanks, Sylvestre, for this wonderful talk and results. I was wondering about PDS 70. Mm-hmm. So you do not resolve any circumplanetary disks, but with ALMA, there is an extended emission around PDS 70b. So what are the constraints that you can put on this extended material or the circumplanetary disk?
So it's a molecular emission they see on ALMA. So and what we are looking at is either thermal emission and scattered light. So it's quite a different physical process. So I didn't look into that, but maybe there's a link to be done between the two of them. Good question. Yeah. But it won't be easy because we're not looking at the same thing.
All right. Thank you.